Hello everyone, I'm Brian Catanzaro, Vice President of Applied Deep Learning Research at NVIDIA, and welcome to GTC. Today I'm going to be talking about generative AI demystified. And generative AI is definitely having a moment. Just during the past few months, we've seen applications of generative AI in image synthesis and in language modeling that have really captivated the world's attention. One really prominent model was the stable diffusion phenomenon that happened, where we started seeing people creating images of all sorts of interesting things and started seeing a lot of applications of image synthesis that were new and a bit of fun. For example, I made a bunch of avatars of myself, and I think a lot of people were really enjoying the new capabilities of image synthesis with generative AI. We've also seen ChatGPT become the fastest growing application in history, with only taking 2 months to reach 100 million users. And here I asked ChatGPT to say something about NVIDIA GTC, and it was able to understand a little bit about GTC and why we're having it, and the ability of these systems to understand questions and do problem solving is just really extraordinary. So that's why we're all here today. You guys have played around with these systems probably and are excited about them. But what we're going to be talking about is, what is generative AI, how's it built, and where's it going? So let's get started. The deployment of generative AI is happening at a rapid pace, and it's really happening in a profound way. Just over the past few weeks, we've seen Microsoft reinvent search by integrating AI-powered copilots into Bing and Edge. We saw Meta announce a new top-level business group that is focused on generative AI. And we saw announcements from Google about how some of their main products are going to be changed through generative AI models that understand questions and can help us answer them. And there's a raft of startups and other companies that are figuring out new ways of using this technology in their own work. So this is the moment for generative AI to really change the way that we do our work. And it's very exciting. There's a lot happening. Generative AI is making new tools for all of the most important work that we do in every different aspect of the economy, in every field. So in education, generative AI is going to change the way that we learn. It's going to change the way that we explore ideas. It's going to help us brainstorm. I don't know if you remember back when you were a student and you were told to write an essay, and sometimes you run into writer's block. Well, generative AI is going to help us get through that, because we'll be able to ask a question to the AI about a topic, and it's going to come back with some ideas, some of which are going to be interesting and will resonate with us, and then we can elaborate on those in order to move forward with our work. It's going to give us feedback, so it's going to help us in real time understand the strength of our arguments and maybe the success that we're having in conveying them to other people. When we think about healthcare, it's going to help us walk through flow charts of what we might be experiencing to better understand what kinds of actions we should take with our medical professionals to improve our health. It's going to help the industry find better treatments, new kinds of chemicals that can be used to treat different problems. It's going to help analyze various health conditions and help us come to a better picture of our health. When we think about biology, we need to be able to understand large volumes of data, whether that's in protein structures or in genomics. And generative AI is going to help both with analysis as well as synthesis, where we can deeply understand the information we have and then use that to synthesize new things that can help us. Agriculture, there's so much involved in agriculture, from data analysis to remote sensing to robotics that are emerging. It's going to help us be more productive there. Or things like programming. Those of us that write programs for a living are already finding that these tools help us be more productive when we're debugging, when we're documenting, and when we're trying to build up scaffolding for what kind of code we should write and how it should all fit together. These tools are also going to help in many other areas, like, for example, writing. So many of us write for a living, whether we're just writing emails to friends or whether we're writing content for other people to read. When we think about marketing and the ads industry, there's going to be personalization at a level that we've never seen before. That's going to help people more effectively communicate the benefits of the things they're building through personalized images and text. Robotics. Robotics has been a dream of the artificial intelligence industry for a long time, and these models are going to help make robotics more useful, help with planning, help with sensing, and geosciences. We have an increased need to understand the Earth and things happening on the Earth, our weather and climate, understand what's on the Earth, the biosphere, the geosphere. These tools are helping with that, or even design. When we're trying to build things, whether that's architecture or web design or product design, these models are going to help us brainstorm about our ideas and put them in context so that we can understand them in relation to the things around them and hopefully make them more useful. So generative AI really has extraordinary different kinds of applications for every aspect of what we do as a society. And I've just been brainstorming with you here a little bit, but the applications are quite profound and go into every kind of work that we do. So let's talk a little about what is generative AI. When AI first started, we were mostly focused on classification, and the goal of a classification model is to make a decision about something. It could be, for example, classifying a picture. So I have this picture of a gecko, and the goal of the model would be to say, what is in this picture? Is it a goose? Is it a glove? No, it's a gecko. That would be classification. And the goal is then to make a decision about some variable, we'll call it X, that's a multidimensional vector, could have a lot of different entries in it. So for example, a picture, if it's a megapixel picture, it has 1 million pixels, and each of those pixels has 3 colors in it. So that's like 3 million dimensions in a megapixel image. So these data points that we're reasoning about, they could be complicated like a picture, they could be something like a document, they could be an audio file, or they could be video. But the purpose of classifying is just to make a decision. It's kind of to understand and analyze, and then sort of boil down data into a result. And that's where AI started. Generative AI goes beyond that. The goal is to understand the distribution of the data. And that could be quite complicated because these are very highly dimensional spaces. And once we have been able to model that distribution, then we can sample from it in order to generate a new example from that data distribution. So for example, on the right here, I have a bunch of images of faces. And if I wanted to synthesize a new face, then I would need to just sample from that distribution if I was able to learn it. But the central problem then in generative AI has to do with learning data distributions. And we do that through deep neural networks. Just a little bit more about this. So we know that the structure of data is captured in its distribution. So for example, if we were just to sample random images from this highly multidimensional space of, let's say, 3 million points to come up with a megapixel image, almost all of the image, almost like 99.999% of the images are going to be random noise with no structure. It's just going to be kind of fuzzy, like a TV back in the old days. The number of images that actually contain something from the real world or some sort of structure in it that we can perceive and understand is almost vanishingly tiny. And those are the images, of course, that we're interested in. And so if we had strong models for learning the structure of data, we could then generate new data. And this is a really powerful idea, especially because we can construct these distributions in order to be conditional on things that we know that we want to use to influence the generation. So we want to be able to control the output and make the output solve a problem for us. Then we can describe the problem in the form of conditioning to this distribution and then sample from the result in order to get one of the many possible solutions to the question that we're asking. It turns out that today's models can absorb truly astounding amounts of data. So for example, if we're making an image generation model, we can train it on billions of images. And if we're training a language model, we can train that model on trillions of words. And they can absorb it not just by sort of understanding it at a surface level, but they can actually build up internal representations that deeply understand the structure and the meaning behind all of these data points that they're being trained on. And that's what enables generative AI to solve new problems. And that's why it's so exciting. So let's look at it a little bit more. Generative AI has been a hot field for a long time. I remember back when I was in graduate school, generative modeling was all the rage, and that was more than 15 years ago. So there's been academic research in generative AI for a very long time, but it's only until recently that the promise of generative AI has really started to break through into the mainstream. And just as an example of this, here's a diagram of the history of the GPT models from OpenAI. GPT stands for Generative Pre-trained Transformer, and it's a particular approach for training a language model to understand text. The first version of this came out in 2018, and it was actually designed to solve fairly simple language processing tasks, like, for example, being able to understand which part of speech a particular word is in a sentence, like is it a noun or is it an adjective. And the way that they did that was different than the ways that people have done this in the past. In the past, we had a more classification-oriented approach where we would try to train a model to predict, for example, is this word a noun or an adjective. But with the problem with that kind of classification approach is that we don't have enough data to train a really good model, because there's just not enough labeled examples of the parts of speech of different kinds of words to build up something that is accurate enough for what we want to do. And so the idea behind GPT at the beginning was we're going to train a model on just a vast amount of text. And the model's going to learn the structure of text so well that it's actually very easy for the model to answer simple questions like, for example, what part of speech this word is, because it has a much deeper understanding of the meaning of the text since it has been trained on so much more data. And so this is a form of what we call unsupervised learning, where we're building models that can really absorb vast amounts of data and then using that capability to solve new problems. But when GPT started, it was fairly simple. It was mostly oriented at improving accuracy on fairly straightforward language classification tasks. But that was not the end vision of GPT. So with GPT-2, which came out in 2019, we really started to see some amazing text generation capabilities. It was expressive, it was long form, it was coherent. You could ask it to tell a story, for example, about unicorns in South America. And it came up with all sorts of details that were coherent and consistent over a long form essay, which is something that we hadn't been able to see from a generative model before. Generative models in the past just weren't able to model sort of the long-range dependencies that are necessary in order to have a coherent structure in the text that's being generated. So GPT-2 was a really big step forward in that regard. But GPT-3 that came out the following year was maybe even more exciting, because the model got dramatically bigger. It was about 100 times bigger. And because of that, it was able to start doing problem solving. So zero-shot and few-shot problem solving, I'll explain what that is in a little bit more detail in a second. But we started to see that the language model is not just a tool for understanding text, but actually a tool for solving problems. Building on that, there was a series of improvements to GPT over the following year or so. WebGPT showed how to use language models to incorporate tools like web search, which then, of course, dramatically expand the reach of information that these models can access. Without accessing tools, these models have to store all the facts from the training set that they learn as a process of trying to understand the structure of language in their parameters. But with the ability to use tools, these models can then reach out to external sources of information or external sources of action in order to solve problems. InstructGPT showed that we could get dramatically better problem-solving capabilities and also align the model so that it better follows human values and principles by using feedback from humans in the loop in order to train these models. And then ChatGPT, which came out at the end of 2022, is where that model was extended to better understand multi-turn interactions and really where we saw it hit the mainstream with extraordinary interactivity and text generation capabilities. So although it maybe seems like we're having this moment of generative AI where all of a sudden we're seeing these applications just pop up and they're so surprising, the field has actually been working toward this for a very long time. And, we believe that there's going to be a lot more progress yet to come. So I want to talk about language models in more detail. One of the reasons that language models are so useful is that all human activity is described by language. So everything that we know how to do, whether that's solve math problems or play sports or the legal structures that we have, are all encoded in language. And we do that because language is compositional. So the words combine in order to form new meanings, and we can express ourselves. And we can use that to convey ideas. We can use that to do problem solving. If you remember taking a test, the teacher writes down the question that you're supposed to solve, and then now it's up to you to provide an answer. Because the question and the answer are both described in terms of language, if we had a model that was able to understand language really, really well, then we would have a model that can actually do problem solving. When we're training a language model, there's a few ways to do it, but it's usually fairly straightforward. One of the most common ways to train a model is just to predict the next word in a sequence. So down at the bottom here, we have a few words from a Disney song, The Wonderful Thing About Tiggers. And if you notice at each step, we choose a word, and then there's a whole bunch of different words that could follow that. So the string of words, The Wonderful Thing About Tiggers, that's one particular sampling from the language model, but there could be many, many others. And so the goal of the language model is, given the past words in some sort of document, predict what the next word is. And because this is such a straightforward training objective, we can apply it to all the text that we can find on the internet. And it doesn't all have to be in the same language. It could be computer languages. It could be all the different kinds of human languages. And so we can gather all of the text from the internet, and we can train the model to predict the next word. And if the model is able to do that accurately, then we know that the model is actually understanding the content of the text and is able to build up some internal structures that correspond to the content of the text and actually start to reason about that text in order to produce the best prediction for the next word. And maybe you have experienced this if you've ever used next word prediction on your phone, if you're typing a text, for example, and the suggestions that it gives you are often just not very helpful. And that's because the models that are currently being used in your phone for next word prediction don't actually understand what you're trying to say. But if you had a model that understood what you're trying to say, then you could imagine it could be dramatically easier to build a model that was useful for that task. Now, one other technical detail that I think is worth mentioning is that the models don't operate on words directly, and you would expect that that would need to be the case if we're training a model that can understand text in every language, since there's many different kinds of words in many different languages, and the definitions are all different. And computer languages are even another thing altogether. So how do we unify these? Well, we build what we call tokens, which are basically subwords, like parts of words. And we do that by looking at our training set, trillions and trillions of tokens, and sort of figuring out what the most important tokens are. We build up a vocabulary of these subwords, which might be like half a word or so. And then we have sort of a general purpose representation that can encode text efficiently. And that's how we train these models. Okay, so I was talking about few-shot learning and zero-shot learning, and I want to describe what that means a little bit. On the left, I have an example of a few-shot translation question. And so the idea is here that I'm going to describe my problem with a few examples of problem solution. So here, what I'm saying is I'm writing a sentence in English, and then I give the sentence, and then I'm writing the same sentence in Spanish, and then I give the Spanish example. And I do that a couple times. And then I ask the model to translate something from English to Spanish by giving it an English sentence and then saying, Spanish, and then let the model complete the sentence. And that is a few-shot translation setup because I've given the model a couple of examples, and then the task of complete the text, it is more obvious to the model that I'm asking it to do translation. Now, the thing is that's so amazing about few-shot learning, the fact that language models can be few-shot learners, which was shown by the GPT-3 paper in 2020. The thing that's so amazing about that is that this model hasn't been trained to do translation at all. It's never been shown tons of examples of parallel texts like you might expect with a traditional translation system. It's just been trained on vast amounts of text from the internet. And in order for it to understand that I'm asking for a translation task to be solved, it has to know a lot of things about language, the structure of language, the idea that there's an English language and a Spanish language, and that there are separate languages with separate vocabularies and separate grammars, but that there's a correspondence, even if it's not one-to-one, and even if it's not even a sort of linear correspondence between these languages. And then it has to understand that when I say English and give it a sentence and then Spanish : and stop giving it any more information, that I'm asking for it to do a translation. And then it has to use all the things that it knows about language, the structure of language, the vocabularies of English and grammar, English and Spanish, in order to actually do that translation. So few-shot problem solving is actually quite amazing. When I first saw one of our language models at NVIDIA doing few-shot translation, I was kind of amazed, just because I felt like this was such a high-level task. If a model can learn how to translate between languages without ever being explicitly taught anything about the fact that languages exist and what their vocabularies and grammars are, imagine all the other things that it could do. And so that was really exciting. But since then, we've gone beyond that, and now with ChatGPT and the things that are following along with state-of-the-art language models today, we're actually seeing zero-shot problem solving really showing up, and that's even more exciting. And so, what's the difference? Well, if you look on the right, I have an example of zero-shot translation, and what I'm doing is explicitly asking the model translate, and then I give it a quote from English to Spanish. And then I let the model complete, and it just gives me the answer. So the reason this is called zero shot is that I've given it 0 examples of what I'm expecting it to do. I just described the problem. And then the model is general enough that it was able to understand the problem that I was asking without ever being given an example directly by me. And so that's zero-shot problem solving, and it's incredibly valuable. When we're thinking about the different ways that language models are being deployed to solve problems in all these different fields, like I was talking about at the beginning, the fact that these models can do that without being given a bunch of examples of what needs to be done makes them just so much more universally applicable. And that's only possible because of the huge amounts of data that these models have been trained on, and the sort of the expressivity of the neural networks that are being used to understand the structure of language. Here's another example of zero-shot reasoning that I found on Twitter the other day. Someone named Zach Witten was talking with the language model that's being deployed in Microsoft Bing, and it turns out that this model actually can play chess. So on the right, you can see a video of the game that's going on, and somehow this model is able to make legal moves, which are usually good. It can explain the reasoning behind them, and according to Zach, it actually has some flair for the dramatic, so it kind of makes some interesting moves. And if you look on the left, you can actually see what that looks like. So he's describing the problem in text. He's saying, tell me the remaining moves in a chess game, and then he's giving it a bunch of moves in sort of the code that's often used in text to describe chess. It's kind of like a language that's specific to chessboards, and then asking the model to complete the game. And it turns out that the model is actually able to do that. Now, in order for a language model to be able to play interesting and legal chess moves, the model needs to be able to implicitly build up a representation of the state space of a chessboard, and it needs to understand, what is legal in that space, and then manipulate it. And the fact that the model's able to do that without ever being trained on chess, it has been trained on enormous amounts of text, a lot of which include data about chess and include the custom sublanguage to describe chessboards. So it's seen things about chess before, but it's never been given the objective become good at playing chess. But because the language modeling task is so powerful and so general, in order to do language modeling, it also had to figure out how to play chess. And somewhere inside that model, there's a representation of a chessboard that's able to be useful to play new games. And this game, is not a game that was just on the internet. So it's not just that the model is repeating and has memorized the moves for a particular game that was really famous and then is just playing them back. That's not the case. The model is actually reasoning about it, has its own internal representation. And I think that's pretty profound if you think about it, that it's possible for a model that's trained on such a general task of just predict the next word to learn how to do something very specific like playing chess. That's just kind of extraordinary. And when we think about all the different kinds of ways that we would like to apply these models, it becomes a lot clearer that these models might actually succeed at solving a lot of problems because of this generality and their ability to reason. Now, another thing that's emerging and I think very important about these language models is that they can be trained to use tools. And the way that this happens is that you can describe in the training text, especially in the fine-tuning text, which we'll talk about in a second, you can give it some examples of what does it look like to use a tool. And there's lots of different kinds of tools. For example, using web search in order to generate citations that might contain links to factual resources that you can use to actually check to make sure that a particular fact inside of the generation from the model is correct. But it could be more general than that. It could include running various actions in complicated programs like Adobe Photoshop or 3ds Max. It could include instructions on how a robot should navigate or problem solve. It could include the ability to write computer code, like let's say, for example, writing a Python script in order to solve a problem. And so you can see that because language is compositional, because we can use language to express new thoughts and new ideas, we can also use language to describe how we can use tools. And we can use language to describe any tool. And then we can train the model to actually pick up those tools and start using them. Then that means that we can start composing the tools that we have, all of the different kinds of tools that we have for manipulating information using language models. And I think that's very exciting and something we're going to see a lot of in the future. Okay, so I mentioned fine-tuning. Let's talk about that a little bit. So when we are starting with a language model and we do what's called the pre-training step, we train the model on vast amounts of data, trillions and trillions of tokens, in order to understand text in all of its different forms. But it turns out that understanding text in all of its forms is not necessarily the best tool for doing problem solving. One of the reasons you can see that would be the case is that text on the internet isn't written as a sequence of problem-solution pairs. You know, when you go to a news article and read it, it has a headline and it has the body of the article with all sorts of facts in it. But what it never contains is like the problem statement, maybe from the editor of the newspaper, that says, please write an article about, you know, the most recent climate change negotiations that were happening at a UN summit. And it needs to include the following facts, and you know, it needs to be this long. You know, none of those instructions are included in the text that you read online. The instructions are usually implicit. And so what that means is that the models, if you just pre-train them on all the text on the internet, aren't actually as good as they could be at following instructions and doing problem solving. And so it turns out that we can influence them by carefully adding human feedback so that the models become much better at problem solving. And you know, one example of this, again, comes from OpenAI. This is from their Instruct GPT paper, where they describe a three-stage approach to this. The first stage is that we collect demonstration data, and then we fine-tune the model in order to make a policy that is going to follow that data. So for example, we're going to actually get a bunch of problem statements and then the solutions to those problems written out by experts who actually know how to write those solutions. We get a small number of those, a relatively small number, and we fine-tune the language model so that it has seen that its primary job is problem solving. We're going to give it a problem, and then we're going to give it a solution. So that's the first step. Then once we have the model that's like a little bit better at problem solving, then we can bootstrap making the model even more powerful at following instructions by using humans. Rather than to write instructions for the model, we actually just ask humans to rate the outputs of the model and to say which one's the best. So once the model starts to show some signs of life, and some of the time it's doing good, some of the time it's doing bad, then we can just rank the outputs from the model and use that to refine the model, use that to refine the policy. So that's the second stage. And then the third stage, we can use what's called reinforcement learning to actually sort of play the model against itself. So we sample a prompt, we generate an output, we then use the reward model to see whether that's a good output or not, and then use that to update the model itself. And so the model basically starts playing against itself and starts being able to generate responses that are even more useful. And so this is, I think, a really important way that these language models are being brought to different kinds of problems in different domains is through the use of supervised fine-tuning and reinforcement learning with human feedback. It's also noteworthy that this process can make the model not just more useful, but also safer. So aligning the model with human values is challenging. You know, these models, because they see all of the different kinds of language, they see language that's objectionable as well. And sometimes they're exposed to biases that exist in text just because humans have expressed biases in text on the internet, and the models pick those up. We would like to be able to influence the model so that when it generates output, that it's generating output that's in line with our values and not just the things that it saw on the internet, because some of those things, you know, just aren't appropriate. And so it turns out that the same technology that makes the model better at following instructions, we can also use to make the model safer and more aligned with our values. And I think that's really interesting. There's often been this tension in research around AI models that is sort of this idea that if we wanted to make the model safer to use and less objectionable, that it was also going to be a less powerful model. But with this approach that we're seeing now, it turns out the opposite, that because we're able to instruct the model to be more aligned with human values, we're also able to use that same approach to instruct the model to be better at problem solving, so the model can actually be more useful to us rather than less useful. So I think that's really important. Okay, so I've been talking about language, and now I would like to talk about some other things. Text-to-image models have been really exciting. Image-to-image models where we can resynthesize images and edit them. We're also seeing a lot of text-to-3D models. So for example, this 3D object was created with a text input saying, make me a 3D model of an astronaut. When we're thinking about the omniverse, when we're thinking about virtual worlds and how people are going to interact with each other to solve problems in the omniverse, it seems clear that generative AI is going to be a big part of that, because this virtual environment is going to be populated by content that we create using generative AI. Generative AI can also apply to other forms of data, for example, speech and video. Here's a couple examples of speech. The first is where we've taken a small amount of data. We have a TTS model, a speech synthesis model, that's been trained on a vast amount of data from thousands of speakers. And then we can take a small amount of data, say, for example, data from my voice, where I spend a half an hour recording in a studio to get a custom voice, and then resynthesize, let's say, my voice in English, the language that I'm natively speaking, but then also allow me to speak in a new language. So here's a sample of speech synthesis in the native language of a speaker that was given just a small amount of data.
They say it's darkest before the dawn. We've been in this town for far too long.
And then without having to teach that person how to speak Hindi, we can enable that person to speak in Hindi using another generative model.
खुदी को कर बुलंद इतना कि हर तकदीर से पहले खुदा बंदे से खुद पूछे बता तेरी रजा क्या है.
So there are many different forms that generative AI can take, many different modalities. And the interesting thing is that they're starting to compose and conjoin. So I was talking earlier about how language models can use tools. Well, we can also connect language models with image synthesis models, 3D synthesis models, speech synthesis models, video synthesis models, in order to make models that can understand and synthesize content in all sorts of different modalities. And I think that's going to be a trend for the next year or so. And how does this composition work? Well, the composition happens through embeddings. And I'm going to give an example from image embeddings, which are able to connect images and text. This one, again, comes from OpenAI. It's called Clip. And the idea is that if you are able to collect a large training set of images with captions, maybe just very simple captions that describe what's inside the image, you can do a training step where we create an abstract space that's just a bunch of vectors, where we project each of these images and each of these text examples into the same space using a neural network. And then when we train the neural network, we are actually training it so that if you have a label for a particular image, that it has the same embedding in this vector space. But if you have an image and a label that don't belong together, then they should have a very different embedding in the vector space. And so that's a very simple rule to train a neural network. Like, are these things the same? Then try to make their output the same. If they're not the same, try to make their output different. And we can describe that mathematically and then train a model on a huge amount of data. And then we have an embedding. So then when we want to actually use this embedding, we can use it with text. For example, we can take that text and embed it into the space. and then we can use an image synthesis model to go from that embedding space back to an image. Or we can do it the other way around. We can use an image and put it through that space and get a vector out of it that then can be turned into text, which we could then use, for example, to understand the contents of images. And because these things are all very general, you could imagine these being composed into neural networks that actually can understand and generate data from all sorts of different kinds of domains. And this is made possible by vast amounts of data. So for example, the Lion 5B dataset contains about 6 billion images with text. About 2 billion of those images are actually paired with English text that describes what's inside. About 2 billion are from 100 other languages. And then there's about 1 billion images that don't really have a language attached to them. It's just, like, for example, the name of some object, which isn't really specific to any language. And so this just gives you a sense of the scale of the data that's required to build these foundational models that are able to embed text and images into the same space. But now that we have those embeddings, then we can start to do some amazing things. And here's some examples of text to image generation from NVIDIA's Edify models that we've been working on. I think these models are so exciting because they allow us to explore new ideas using visually explore new ideas using text. And for those of us like myself that are not artists, it's really quite challenging to come up with new images that describe ideas that I'm thinking about, because I just don't have the technical skill to paint. But these models are actually able to compose ideas and then generate images of new things that I might be interested in. But the models can do more than just text to image. Here's an example of using the model to actually control the output of the image. On the left, the person is drawing kind of a cartoon of where different kinds of objects go. And the number of different kinds of objects is unlimited because each of those objects are just being described using language. So for example, there's the rabbit mage, there's a fireball, and then the rabbit sitting on clouds. And then the text that goes along with it describes the entire scene, but we're controlling it with this cartoon that gives the model an idea of where something should go. And so this is an exciting new capability for these image synthesis models, because now I can actually build images where things are in the positions that I have chosen. And again, this all happens through the magic of these huge models and huge embeddings. These models can also synthesize things using style references. So for example, we're going to take a famous painting from Van Gogh along with some text that describes a scene and use that to synthesize a new image that has all the elements that we wanted but looks like another image. Here's some outputs from the Magic 3D model that NVIDIA has been working on. And this is pointing to these models working in other spaces besides images. In this case, we're making 3D geometry. And you can imagine that these 3D objects could be painted with textures and shadows and materials that were derived also from generative models in order to create new kinds of objects that could go into a virtual world like the Omniverse. Okay, so I've talked a little bit about what generative AI is. I've talked about some of its applications. I've talked about some of the technologies that are used to build it. Now I'd like to talk about some of the challenges and some of the things that I think we still have to work on before generative AI is fully deployed. One of them, obviously, is that generative AI is often wrong. So when we look at the output, whether it's an image or a video or text or anything else, the models are often very confident. They're producing things that are plausible, but they might be very incorrect. So for example, if you ask a question to one of these models, you're not guaranteed to get an answer that's factual. And that's a problem when we're thinking about how these models are being deployed. And I think the research community is coming up with a lot of different ideas to make these models more factual and more reliable. And we're going to see a lot of progress along those lines. One of the reasons I'm so confident about this is just that I've been working in this space for long enough, and I've seen the extraordinary amount of progress that has happened over the past 15 years in order to get us where we are today. And I think we've overcome just such enormous challenges to make the models that we have today. And I think we still have enormous challenges to fully develop the promise of these models. But there's so many smart people working on this. I think we're going to see a lot of progress. The training data is also really important and is a challenge for generative AI. So in a number of ways. One of the problems with training data, we're building these models by collecting as much data as we can from all the different sources we have access to. But there's going to be sort of correct data and incorrect data. There's going to be biases in the data because that's what happens on the internet. There's all sorts of qualities of data and different ideas that people have, some of which are correct and some of which we disagree with, some of which are harmful and some of which shouldn't be expressed. And so how do we find all of that? How do we sort it? How do we make the models robust against that? That's really important. And then, of course, how do we correct for biases that we find? But there's other challenges as well. One of the things that is, I believe, true about data is that the more valuable a data set is, the more proprietary it tends to be. And that needs to be so. For example, medical data is very valuable, but it needs to be kept private because we've agreed as a society that medical data shouldn't be just randomly shared on the internet. And that's really important to us. And so it's not a good idea to train a model on all sorts of proprietary data that should be kept confidential because we don't know how to train these models to keep secrets. We don't know how to train these models how to observe confidentiality. And so that means that there's going to be a need for these models to be specialized in sort of private ways that allow the models to solve problems in new areas that are enabled by proprietary and confidential data, but that maintains the confidentiality of that data. And I think that's a big challenge for generative AI, and we're going to have to do some work to figure out how to make that happen. We also have other pretty significant challenges as well. So IP ownership, there's been some controversy, maybe you have seen some of it, about some of these image synthesis models that have been trained on all of these 5 billion images from the web. The problem is that some of those images, the artists or the photographers or the people that created those images would really prefer that their image not be included in one of these models, because if the model is able to extrapolate or reproduce something that reminds a creator of the work that they've done, but they're not getting credit for it, or they haven't consented, then that's a big problem. And this also has to do with a lot of commercial applications. So, for example, if you're building a model, let's say, for example, that's doing personalized advertising for your particular brand, you want to make sure that the model is only going to output images and text that correspond with your brand identity and your brand values. So, for example, if you're making a model to advertise for Marvel Comics, it would be really bad if the model started advertising for Disney, because that's not what you've built the model to do, and also it would be a violation of copyrights and trademarks. And so there's a lot of challenges regarding these models, because the way they get their power is by being trained on such large amounts of data. But that also means that they can sometimes be difficult to focus, and so it can be challenging to prove that a model is going to be safe to use and is going to reflect the purpose for which it was designed. And so we have a lot of work to do, both in terms of training custom models that are more restricted but still useful, as well as building in safeguards so that the models are more controllable, and also aligning the models with human preferences so that they're safer to use. So this is going to be ongoing work, and I don't think that it's easy work, and I don't think it's ever going to be fully completed. But at the same time, I know that we're making a lot of progress, and we're finding more and more applications where we can be confident that these models can be deployed. One of the biggest challenges with generative AI is training and deploying the models, because they have to be trained on such a large amount of data, and the models themselves are quite large and have a lot of parameters. So NVIDIA has been working with the rest of the industry for a long time in order to optimize every part of the stack that's necessary to train these models. And I'd like to talk about that in a little more detail. So NVIDIA NeMo is our collection of frameworks for training models for the enterprise, and we have been optimizing its language model training speed very significantly over the past few years. For example, when we're training large language models, we can get above 50% of the theoretical peak speed of the tensor cores of the machine when we're running on thousands of GPUs at once. And that's an extraordinary achievement that required work from thousands of people at NVIDIA and across the industry in order to optimize every part of the stack. The tensor cores, the processors on the GPU, the caches, the memory subsystem of the GPU, the interconnect between GPUs inside of a box, the CPU-GPU connection, the software that's running between them, the networking in between boxes in a data center, and the entire data center architecture. The frameworks, the application frameworks, all of that has a ton of technology that comes together in order to provide transformational speedups for language modeling. And we've been investing for a long time in not just performance, but also flexibility for these frameworks, because it's not enough to have software and hardware that work together to train the model of the past, but we need to enable people to train the model of the future. And if there's one thing that we know about generative AI, it's that it's changing rapidly. And the systems of the past, the models of the past, are not the same as the models of the future. And so we have been working really hard in order to provide both incredible efficiency as well as incredible flexibility for researchers building the technology of the future. Deploying generative AI is also a huge challenge. And perhaps some of you have experienced this when using some of the demos and prototype systems that are out there. The speed that it takes to generate an image or to generate text can actually slow down the way that we use them and add friction. And it's clear that if we were able to reduce the time that it takes to generate samples from these models, then we could actually see these models more widely deployed. It's also interesting that in the past, we've designed systems with training as the main focus, because the goal was to generate technology that had never been created before, and that required an enormous investment in training. But now that these models are starting to be widely used and they're so general, we're starting to see that the compute is shifting towards inference. And that's an exciting challenge, I think, for the industry to figure out how to make these models as efficient as possible to deploy so that they can be deployed as widely as possible. And perhaps you've heard of the Jevons paradox. It's this idea that if you can make something cheaper to use, then the aggregate demand is going to increase. And that's been observed in many different fields in economics over the centuries. And I think it applies to generative AI as well, which means that the scale of application of these technologies is going to be super linear as a function of the efficiency that we can deploy them with. So if we can make it just a little bit more efficient to deploy, there's going to be dramatically more new applications for this technology. Sometimes it's even better to use an API rather than deploying a model yourself. And NVIDIA is working on that as well. We've been talking about some of the APIs that we're creating for NeMo and Picasso and BioNeMo. And these models are running in various clouds. that we can provide access to. And, I think going forward, we're going to see lots of companies, including NVIDIA, investing in building APIs and infrastructure for various companies to deploy generative AI and customize it for their own business uses. Generative AI is bringing us into a new kind of economy that is a post-scarcity economy for intellectual work. It's shifting our efforts into a higher level of abstraction. The amount of content is becoming less important. Maybe you remember when you were in school, your teacher would say, please write a 10-page paper about something. Now, why did they ask you for 10 pages? Well, part of it was reflecting the truth that in order to express an important idea, it needs to be fully elaborated, and that takes up space. Part of it was reflecting the work that's required in order to actually come up with ideas that could fill that space. And so many of us were used to the idea that the size of the content that we created was correlated with its value. And I think, that's true, and it still remains true. But it's also the case that in a world with generative AI, where we can create content, whether it's text or other things, very easily, the size of the content is going to be much less important than the value of the ideas, the quality of the ideas. And I think that's an exciting development. I think what it means is that instead of thinking so much about, have we been able to produce a certain amount of content, we're going to be focusing more on the purpose of that content, what it means, how do we react to it, does it resonate with us, what does it teach us, is it factual, is it correct, is it arguing something that can teach us something. And I think that having tools for us to augment our ideas and elaborate on them with AI is going to help us explore our ideas more deeply and then ultimately learn new things as a society. So I think that's going to be really exciting and important. It's going to yield more productivity for all of us that are doing intellectual work. We also have to think about what the framing for the model is. I've seen it many times when deploying AI at NVIDIA that the difference between success and failure for a particular model can depend on the inputs and the outputs to the model. The model itself might be a good model, but if it's deployed with the wrong input, it's going to yield bad outputs and it's going to be insufficient for the task. And generative AI is no different. There's an enormous amount of work that goes into figuring out how a model can be deployed. Sometimes we call part of this work prompt engineering. So with any of these text models, whether it's text-to-image models or language models, there's various ways of posing the question. There's various instructions that you could give the model in text in order to tell it what you want and influence the result. And the process of exploring how to describe instructions to the model in order to get the result you want, and how to prepend instructions that help people solve particular kinds of problems in particular domains. We call that prompt engineering, and that's pretty important. For a lot of the images in my talk, I've been using a generative model, and the quality of results that I get from the generative model really depends on the quality of the question that I ask. And so there's a new kind of skill, a new kind of creativity that comes in interacting with these models, where you figure out how to ask questions in more useful ways, and that is going to be valuable. People that play with these models and kind of learn how they work are going to be able to get more done with them. We also have a lot of investment going into guardrails, and this is kind of models maybe that surround the central model, or heuristics that provide more safety, more fact-checking, more control over IP ownership. And I think we're going to see more investment of these over time as well. The central challenge of generative AI is control. You have a very powerful model that can generate anything, but you only want it to generate some things. It's hard to say exactly what you want to generate it. How do you describe to the model? How do you create an environment where it's safe to use that model? That's the central question that we're working on, and there's a lot of investment going into guardrails around the model. And I always think it's worthwhile to remember this quote from George Box, who is a famous statistician, who said that all models are wrong or some are useful. And the question is, how do we make these generative models useful? There's a lot of work that goes into how the model is deployed that doesn't actually have to do with the model itself, but the framing around it that's critical in order to get something that actually solves a problem. Generative AI is really having a moment. People from around the world in every different domain are starting to see generative AI change the way they think about the problems that they solve during their core day-to-day work. And it's really exciting. It's an exciting moment for artificial intelligence to see new kinds of applications. It's a little scary because things are happening fast. There's a lot of change. And there's risks that we have to manage. We have to think through responsible ways of creating and deploying this technology. And overall, I'm an optimist. I believe in the power of progress. I believe that making tools that help people be more productive at their work ultimately is going to help us make the world a better place. And it's going to help us enjoy our work better. It's going to help us get more value out of it. It's going to help us solve problems that we didn't know how to solve before. But for us to get from where we are to today to there is going to require a lot more work and a lot more research and development and investment, and a lot of brilliant people figuring out the right way of deploying this technology to solve their own problems. And I can't wait to see what you all figure out. And I can't wait to continue helping with that myself. So thank you.